session. Puedes poner préstame ese. This is the third session in computer science and computer engineering, and the first work is aerial intelligence for ecosystem protection through AI enhanced UAV surveillance of invasive flora. Speaker is Vijay Sahin. Please start 15 minutes, please.
Hello, I'm starting the presentation now. Can you see me
Vijay
screen?
Sahin.
Can you hear me?
Okay,
hello?
You can start 15 minutes, please.
Okay. Hello, everyone. My name is Behir Şahin, and I am an aerospace engineer from Tarsus University in Mersin, Turkey. Today, I will present my study titled Aerial Intelligence for Ecosystem Protection through AI UAV surveillance of invasive flora. In this presentation, I will explain how drones can help protect our environment by detecting harmful plants in nature. Here is the outline of my presentation. I will start with the introduction and aim of the study. Then I will explain the related works, the system overview, and our datasets. Next, I will describe the image process, model training, and the results. Finally, I will share the discussion, conclusion, and acknowledgements. Invasive plants are one of the major threats to agriculture and biodiversity. They grow fast, take nutrients and water from useful plants, and reduce the quality of.
Your presentation is not updated. We see the title. Perhaps you can roll down your presentation, and perhaps you can raise up the volume of your speaker.
Is my slide processing?
Offline. Okay.
Yes. Outline. Here is the outline of my presentation.
Outline.
Yes, outline. Here is the outline of my presentation. I will start with the introduction and end of the study. Then I will explain the related works, the system overview, and our dataset. Then I will explain related works, image process, UAV time, model training, and the results. Finally, I will share the discussion, conclusion, and acknowledgements. Introduction slides. They grow fast, take nutrients and water from useful plants, and reduce the quality of crops. Traditional detection methods are slow, expensive, and require a lot of manual work. In this study, we use unmanned aerial vehicles, also known UAVs, together with artificial intelligence of the learn automatically. This approach helps us monitor large areas in a short time and with high. Research A slide. The aim of the study is very clear. We want to develop an AI-based UAV system that can automatically detect and map plan spaces using the Lewittan deep learning algorithm. This is also the location on a map using GPS data. Importance of the study. This research is important for several reasons. First, it helps to protect biodiversity and farmlands by finding harmful plants early. Second, it reduces the time and cost of traditional harvest. It supports smart agriculture and sustainable ecosystem management, which are key goals for future environment protection. Related works, many previous studies have used YOLO-V8 and YOLO-V9 for object detection in agriculture. However, in our work, we use YOLO-V10, which is a newer and more accurate version. We also improved the system with RTK GPS mapping, which allows us to research centimeter precision in mapping plant locations. This combination gives better detection and mapping results than before. System overlay. Sorry. Um, the slides are simultaneously. Yes. Okay. System overview. This slide shows the overall workflow of our system. First, we collect aerial images using a DGA Quantum 4 Pro drone. After that, we train in the YOLO-V10 model to detect different plant spaces. Later, we match the detection results with GPS data, and finally, we create geospatial maps to visualize the results. Each step plays an important role in creating a smart detection system. Dataset, our dataset includes 3,114 images in total. About 72% of the images were captured by the drone, and 28% were collected from public databases. We included 8 invasive plant species such as wild mustard, mallow, and dandelion. This combination of real and online data helped the algorithm to learn more general and realistic features. Image before training, all images to make detection more reliable. We use two main methods, Collie and bilateral filter. The bilateral filter reduces image noise but keeps the sharp. With these methods, we improve the image quality and detection accuracy under different lighting conditions. YOLO-V10 model training. For model training, we divided the dataset as follows: 73% for training, 16% for validation, and 11% for testing. We trained the YOLO-V10 model for 250 epochs using an NVIDIA RTX 3090 GPU. We also used early stopping and cross-validation to prevent overfitting. This careful setup helped us reach strong and constant results. Here are the results of our study. The highest F1 score was achieved for Wild Mustard with 83.5% accuracy. The mean map uh, a map mean MAP to 0.5 was 71.6%, which shows high detection precision. In general, YOLO V10 outperforms YOLO V8 and YOLO V9, proving that our model is much faster and more accurate for real-world detection. The detection made by the algorithm were matched with GPS data to create maps. By using RTK GPS, we reached centimeter level precision. This allows us to see the exact distribution of harmful plants in the file. For example, in a current file, amaranthus and sorghum operate mostly along the file edges and irrigation lines. Such detailed mapping supports targeted with control and smarter use of research. This technology can guide farmers to take localized actions like spraying only where needed, saving bad time and chemicals. Discussion. Now let's discuss the main strengths and limits of the study. The main advantages are that the system fast, low cost, and scalable. It provides high accuracy, even in complex environments. However, there are some limitations to weather conditions such as strong wind or rain can affect flight stability. Battery life of the UAV is also limited, and processing large amounts of image data requires strong hardware. Despite these challenges, the system shows great potential for real agricultural use. In conclusion, this study shows that combining UAV with YOLO V10 deep learning can successfully detect and map invasive plant species. Our results prove that this method is efficient and practical for real-world applications. It contributes to smart farming and sustainable ecosystem management, supporting better environmental educations and more efficient field operations. Thank you very much for your attention. If you have any questions, I will be happy to answer them.
Okay, thank you for your presentation, Mihaly.
You're welcome.
Questions? There are some questions. I remember when I read your contribution, I remember when some decades ago, 3 decades ago, two, I wrote one PhD that used the appearance-based images for identifying and
Here,
do the mapping of the area super area for taking care of oil tops. and the used method in this time was using the appearance of the images of the first images and late images. And your work remember me this work, but you used the method you explained, deep neural networks, if I see fine. So you can explain what's this machine learning method you use now could be related with this 20 years ago method that used the appearance of images to distinguish between one image and all. Perhaps you could say something about that.
We provide machine learning using the YOLO method. Some of these images were taken from the web.
Your answer, the answer she gave is all. Your answer. We lost your sound.
I don't understand your voice. Doesn't count.
We didn't listen your answer. Please, maybe you can repeat.
Okay, we provide machine learning using the YOLO method. Some of these images were taken from the web. Okay. Here.
Okay. Okay, no comments, no questions? Okay, thank you for your presentation.
You're welcome. You're welcome.
Okay. I don't know if wait for or no. Perhaps we can continue just now with the next presentation, ID 61. Number is strength and trade-offs of deep learning-based crack detection in smart mechanical inspection. Speaker Zeynep Sahutoglu. Please, you can start. You have 21, 22 minutes now. So 17 for your explanation if you wish. Come on. Send us.
I can hear you, but my screen is not opened. 1 minute, please. Are you here now, my screen? I'm sorry, but 1 minute, please. Are you here now?
Yes, you can start.
Okay. Hello, my name is Zeynep. I am research assistant at the Unmanned Intelligence System Laboratory. Today, I will be presentation stages and trade-offs of deep learning-based crack detection in smart mechanical inspection. I would like to begin by explaining why crack detection is so important. Crack in mechanical parts can damage structural integrity and create serious safety risks. That's why early and accurate detection is essential. It helps reduce maintenance costs and keep operations safe. In this study, we we compared three object detections algorithms: faster RCNN, SSD, and YOLO version 5. Each offers a different balance between speed and accuracy. Our goal was to find out which model works best in instructional inspection environments. According to the results, faster RCNN gave the highest accuracy, recall, and map sources. It was the most accurate model. However, it runs slowly, so it's not ideal for real-time apps. YOLO version 5 was the faster model. It's great for real-time maintaining and still gives competitive accuracy. SSD was faster than RCNN, but its detection accuracy was lower. That makes it less suitable for tasks that need high precision. One important finding was that lighting conditions had a big impact on all models. This shows we need systems that are more robust to environment changes. In conclusion, this study helped us understand which model fits which scenario. In future work, hybrid or adaptive approaches could help us build systems that are both fast and accurate. At this point, I would like to emphasize that crack detection is not just a quality control task. It's a key factor in ensuring operational safety and long-term durability. In high-risk, high-precision fields like military vehicles production, the accuracy of these detections directly affects performance in the field. AI-powered systems offer more than just reduced human error. They save time on the produced line, lower cost, and provide standardized reporting that makes decision-making more objective. This creates a competitive advantage, especially in strategy sectors like defense. Looking ahead, we
Sorry, your slide is the number 2. You're speaking about this slide, or you should roll down?
I can hear you. I can't hear you. Please repeat.
Yes, please.
Are you hear me?
Yes, because we have solved your slide 2, and perhaps you are explaining other thing. Now we are seeing your slide 3. Please, you can continue with slide 3 and then.
Okay. This figure shows how the faster RCNN model detects crack in an image. First, the input image goes through a special neural network called a CNN, which looks for important features and patterns. This helps the system understand what's in the image. Next, the regression probable network like RPN suggests areas where crack might be. These areas are marked with boxes of different size and space. Then the system adjusts these boxes a standardized size so it can analyze them more easily. After that, each box is changed to see if so contains a crack, and the system gives a confidence source to show how sure it is. Finally, the boxes are fine-tuned to better match the exact location and size of the crack. Thanks to this step-by-step process, faster RCNN can detect cracks with high accuracy. However, because it does make steps, it can be slower than other models, which might be a challenge for real-time use. In this figure 2, we see how the details used in the study is divided into 3 parts: training, validation, and testing. Out of a total of 1,865 images, the largest portion, 59%, that's 1,107 images, was used for training. These images help the model learn how to detect crack effectively. 18% or 338 images were used for validation. This step checks how well the model is learning during training and helps prevent overfitting. The remaining 20%, 23%, which is 413 images, were set aside for testing. These are brand new image the model hasn't seen before, and they are used to evaluate its final performance. This balanced speedily ensuring the model is training properly, adjusted, accurate, and testing fairly. It's also help improve the model's ability to perform reliable in real-world conditions. For the third figure, in this figure, we see examples of image processing and data augmentation methods used for crack detection. This first image, labeled image 1, is shown in its original form without any processing. It reflects the natural operation of the surface and serves as a reference point for analysis. The following image include adjustments such as brightness, contrast, and sharpness. For example, increasing brightness makes darker areas more visible, but might choose some detail loss. Reducing brightness makes cracks more noticeable, but lowers overall visibility. Increasing sharpness highlights cracks adjust, while reducing it chooses blurring and makes analysis harder. Contrast adjustment also affects crack visibility. Higher contrast amplifies difference between light and dark areas, making cracks stand out. Lower contrast creates a more uniform image, but can hide important details. Grayscale conversion removes color information and focus on tonal differences, which is useful for analyzing surface textures. Finally, thresholding and edge detection techniques clearly outline the boundaries of cracks, making structural damage easier to examine. Overall, these image processing methods help the model perform better under different lighting and surface conditions and improve the clarity of crack detection. First, table 1. This table comprises the performance of 3 deep learning algorithms: faster RCNN, SSD, and YOLO version 5 in crack detection. 5K metrics are used: precision, recall, map, F1 source, and inference time. Faster RCNN ranks highest in precision and recall, meaning it detects crack accurately and misses fewer true choices. It also leads in map and F1 source, showing strong overall performance. However, its inference time is the longest, which limits its use in the real applications. YOLO version 5 starts out for speed with an inference time of just 21.6 milliseconds, making it ideal for real-time systems. Its precision and recall are better than SSD, offering a balanced performance. SSD is the second fastest, but has the lowest accuracy. It might be suitable for scenarios where speed matters more than precision. In summary, faster RCNN is best high accuracy need. YOLO version 5 is ideal for fast and balanced detection, and SSD is useful when speed is the top priority, but accuracy can be compromised. For the figure 4, shows how YOLO version 5 detection cracks under different surface and lighting conditions. The examples include fine, elongated, multiply, and low contrast cracks. Image A and image B cracks are clearly detected on complex textures and curved surface. In C and D, multiply crack are identified simulations showing the model's ability to handle dense areas. Image F, G, and H demonstrate successful detection on symmetrical and worn surface, proving YOLO version 5's generalization ability, even in cases with Gaussian or color distorting the model performance reliability. Overall, figure 4 visual confirms YOLO version 5's strength in delivering fast and accurate crack detection across varied industrial scenarios. This figure compares the crack width measurement performance of faster RCNN SSD and YOLO version 5 under both poor and educate lighting conditions. The actual crack width is 12.8 millimeter, and the accuracy of each algorithm is evaluated based on how close their measurements are to this reference. Faster RCNN measured the crack as 12.2 millimeter in low light and 12.6 millimeter in good lighting. This shows that the model performs more accuracy when lighting is sufficient. YOLO version 5 measured 11.8 millimeter in poor light on 12.5 millimeter in educated light, also showing improved prevention under better conditions. SSD showed the weakest performance, measuring 11.5 millimeter in low light and 11.9 millimeter in good light. In both cases, its results dividing more from the actual width compared to the order 2 models. Overall, the figure highlights how lighting conditions affect crack detection and measurable accuracy. To conclude, this study has successfully demonstrated the use of deep learning algorithms for crack detection. Among the models evaluated, faster RCNN delivered the highest accuracy and precision, making it ideal for applications that require detailed and reliable detection. YOLO version 5 stood out for its speed and balanced performance, proving to be the most practical choose for real-time systems
So we need to go to the next presentation. Thank you very much for your presentation.
Okay, thank you for your attention.
Yes. Okay. Sorry, because I wish to ask some questions, but okay, no time now. We follow with the next presentation.
Okay.
Next presentation is selecting what matters, a regression-based embedding for variable influence discovery. Speaker is Franco Rivadeneira. Okay, you can start, Franco, please.
Okay. Please, can you confirm if you can see the presentation?
Yes, we see your presentation. Thank you.
Okay, thank you. Okay. Good morning. I'm Franco Rivadeneira. I'm from the Pontificia Universidad Católica del Perú. And today I'm going to present a paper named Selecting What Matters, a regression-based embedding for variable influence discovery, or IVE. In recent years, the explosive growth of high-dimensional data across many scientific fields has posed major challenges for traditional machine learning and statistical modeling. In domains such as bioinformatics, image analysis, and text mining, datasets often contain thousands of variables but very few samples. This course of dimensionality complicates computational and also harms model generalization because of the noise accumulation and feature redundancy. So, to handle this problem, dimensional reduction techniques have become very used and very essential tools in modern data analysis. Among these, principal component analysis, PCA, and linear discriminant analysis, LDA, are the most widely used. To overcome these limitations, the study introduced a novel unsupervised model method named influential variable embedding, or IVE, that, in contrast to the projection-based techniques such as PCA, IVE focuses on quantifying the directional influence of each variable by evaluating how well it can linearly predict all the remaining features. The study provides a mathematical formulation of the algorithm and evaluates its performance against established dimensionality reduction techniques on real-world and synthetic datasets, demonstrating that IVE identifies segmentally meaningful variables that capture the intrinsic structure of the data. Some limitations of the existing methods are the PCA provides global projection but loses interpretability since each component mixes all variables. The LDA have the limitation that need class labels and assumes linear separability, so it can be used in supervised problems. For graph-based or deep learning methods are complex and often lack a clear interpretation of variable importance. So the IVE algorithm starts with, for each variable in the dataset, we check how well it can predict all variables using linear regression. If one variable can reconstruct the rest of with a small error, it is considered high influential. The influence score is computed in a way similar to the coefficient of determination, or R-square, capturing how much variance a single variable explains across the dataset. First, we take one variable and remove it from the dataset. The next step, we have to train a linear regression model where the variable predicts all the others. As you can see, we have to find the minimum argument of this formula, but we can use the closed form least square solution, which is this formula shown below. So the reconstruction of the other variables is then this linear equation. So the matrix X minus I represents the best linear approximation of the remaining variables based solely on the Xi. In the broader context of the I framework, this step operationalizes the concept of directional explanatory power. That is the ability of each variable to predict the structure of all others. Third, we compute an influence score based on the reconstruction accuracy. Let it know the column center version of X minus I. This centering process removes the mean value from each column so that every feature in X minus I has zero mean. Formally, the center matrix is obtained as this formula. Here, this expression represents the vector of the column wise, meaning that the X minus Y, where X minus Y denotes the T row vector corresponding to the T sample. The matrix replicates the mean vector across all the n rows, ensuring that each column of X minus I is centered around 0. This mean centering step is necessary to measure reconstruction quality relative to the total variance of the dataset, analogous to the variance normalization in regression analysis. We then define the inflation score of variable xi as a normalized reconstruction accuracy, conceptually similar to the coefficient of determination. The numerator quantifies the residual reconstruction error of the regression model, while the denominator represents the total variance in the center dataset. Hence, the influence expresses the proportion of variance in x minus I that can be linearly reconstructed for xi. Higher influence score indicates that variables that are more structurally informative and exert stronger explanatory power over the remaining features. So, the top-ranked variables are selected as the most structurally informative ones, and this ranking yields a global view of how each variable contributes to the reconstructing the remaining of the dataset. Variables with higher influence scores correspond to features that carry stronger structural or causal signals within the data manifold. In contrast, variables with lower scores are less informative and may represent noise, redundancy, or weakly correlated dimensions. So the final step, the final subset of the variables is obtained by selecting the key high scoring features, formally expressed as this expression, where the S knows that the set of the selected features indices corresponding to the case most influential variables, and this subset preserves the essential structural information of the original dataset while discarding variables that contribute little to its global organization. So, some IF applications. First, for exploratory data analysis, it helps reveal which variables drive the structure of high-dimensional data, such as genes or sensors. A second application of IF, as pre-processing step, it can reduce the feature set before applying other models, improving interpretability and reducing overfitting. That's because IF selects original variables rather than projection. It preserves their meaning, which is especially useful in fields like bioinformatics or healthcare. So, for this experimental setup, it was tested the IF on the TCA pan cancer gene expression dataset, which contains more than 20,000 gene features and three cancer types. And for a free comparison in this experiment, we select the first 55,000 genes and standardize the data. We compare IF with 4 common methods: the PCA, the kernel PCA for nonlinear datasets, the DSNA algorithm, and the select key best. Each method reduces the data to 2 dimensions, and we evaluate the result using the adjust rand index and the silhouette score, as well as runtime. According to the results of the ADA findings, in the exploratory analysis, I've identified the genes with the highest inference scores. The top-ranked genes were mostly related to the breast cancer and kidney cancer, suggesting that these variables strongly explain the other genes expressions. Also, this shows that IF can highlight biologically meaningful features even without using any class labels. According to the performance, when comparing performance, I've achieved the highest usability score among all methods, showing that it produced well separate and coherent clusters. However, it has a lower adjust rand index since it does not use label information. While TSNE performed based in a just run index, it loses interpretably. IVE takes more time to compute, but it provides interpretable and meaningful feature rankings. So IVE excels in identifying global influential variables, making it a valuable tool for hypothesis generation and data exploration. However, it is more computationally expensive than PCA since it requires one regression per variable. Also, because it is currently used on regularized linear models, it may be sensitive to noise. So future versions can include regularization and parallel computation to improve scalability and stability. Finally, to conclude, IVE provides an interpretable and supervised way to discover influential variables in high-dimensional data. It bridges the gap between dimensionality reduction and feature selection by focusing on variable-to-variable relationships. In the future, it is planned to develop a nonlinear and GPU parallel versions and integrate IVE into deep learning frameworks. Overall, IVE moves us closer to interpretable and scalable supervised learning. Thank you so much.
Okay, thank you, Franco, for your presentation. Please, perhaps there are comments or questions. I have a lot of questions. Please, you can put your first slide of results.
Okay.
Yes, this one, not, yes, no. The one, the next, please. Next, where is the images?
Yes.
The slide with images, please. The first slide of your results. This one.
Okay.
Yes. Because you mentioned that your proposal is in unsupervised machine learning, and that you used some variables to identify the influence that has with respect to others and the converse. However, I don't understand what you refer. And please, next slides. When you next one, please. Yes, this. In this case, you analyze TCGA genes, and here you say that the top ranked genes were mostly related to breast cancer and kidney cancer, and suggesting that these variables, and in this case, variables are the breast cancer genes and the kidney cancer, okay? And explain other gene expression. I don't understand this statement. This, you can explain a bit more?
Yeah. I mean, when I was saying that the breast cancer and kidney cancer suggest that these variables are strongly explained other gene expressions, I'm not referring that is the causal of the other cancers, but if you do a machine learning model, you can identify that breast cancer and kidney cancer can maybe have a correlation between these all cancers, but breast cancer and kidney cancer are the most valuable, how do I say, the most valuable targets. So you can use more of these variables. It's not the causal, but it's very related to these other cancers.
This is the point that I don't understand, because it means that breast cancer is quite influential with respect to other cancers.
Yeah, it has.
Regarding the genes that are present in breast cancer, or what's the influence? Is the point I don't understand. And actually, even more, what's the internal methods that the tools you used? Because perhaps this way I could understand, because this is a kind of black box that you use, that, but I wish understand the mathematical tools inside these tools, and perhaps this way I can follow this correlation you intend to explain on the influence of genes in breast cancer with respect to others.
Yeah. Okay. So the mathematical part starts here. First, we're supposed to have a table with n elements and one target. So you have a lot of dimensions of the data. So joining these dimensions, you can finally obtain a target, meaning if it's a cancer of kidney, it's a hair cancer, something like that. So the purpose of this algorithm is to examine it for each element, how it can be correlated to the other elements in order to predict the cancer. So first, let's suppose we have a one dimension, a column of a gene in specific, and we have to do a linear regression to find the weight, and the weight can be used to compare the error of the real output with the predicted output using these weights. So we can examine using each type of genes to check which is the most influential to the other genes in order to predict which cancer which is the correct cancer you are detecting.
Okay. Okay. Yeah. And you see that there are some methods that use in information theory, entropy in information theory, and mutual information as well. You can see this kind of methods to analyze these correlations between genes or not.
You can only see you can only quantify how this class can be more influenced than another class. Just that. Not the causal, but you can see how much it can influence to the other cancers.
Okay, and it must use here the mutual information that is based on entropy concept.
Yes, in entropy concept.
Thank you, Franco. Thank you very much.
Thank you so much.
Okay, we can continue with the last presentation in this session of computer science and computer engineering. And the last presentation in this session is IoT-based weather and dust level monitoring system in context to Bangladesh. The speaker is, who is the speaker? We can see. The speaker is Nurin Ihlam. Okay, you can start, please, Nurin.
Thank you. I'm gonna share my screen now. Please kindly let me know if you can see my screen.
Yes, we can see. Thank you.
Thank you so much. My name is Norin Islam, and I will be presenting the paper called IoT-based weather and dust level monitoring system in context to Bangladesh. So, as an introduction, the reason why we started working on the paper is because we found that farmers relied on traditional methods and lacked real-time environment data, and this led to inefficient irrigation and delayed pest control and lower crop yields. And for that, what we determined was they needed a low-cost, data-driven system for smart farming. So we try to identify the parameters which the farmers required for a proper IoT-based monitoring system. And one of the major parameters which we identified were temperature, humidity, dust, wind, and light. There were other parameters which could be integrated into a system as well, but we focused on the main parameters that caused the problems in farmers traditional farming systems. So what we try to do is we try to optimize the irrigation, pest control, and crop planning system in real time. So before starting our work, we reviewed multiple papers, and there we saw that there were IoT and sensor networks which were widely used to prove irrigation, resource source, and crop productivity. And those most of them were most of them had a real-time monitoring system which was implemented, and the parameters they used widely was temperature, humidity, and soil moisture. And apart from that, the studies showed that dust and air pollution also harmed the crop health. So that's why we integrated dust as a parameter in our system. But most of the system was considered as very expensive, and which was not suitable for small rural areas in Bangladesh. So our work proposes a low-cost IoT system which focuses on real-time dust and weather monitoring for agriculture in context to our country. So in our system overview, our system used an ESP32 microcontroller as a central unit for data collection, and the sensors which we used were temperature, humidity, light, wind speed, air pressure, and dust. So what the overall so how our system worked was the sensors collected data from the field, and the data were transmitted to a cloud server, and then analytics were shown in a user interface. So this could all happen because ESP32 aggregates all the sensor data and sends it through a MQTT protocol through to the ThinkSpeed cloud. And then again, the user interface is integrated using the ThinkSpeak. So the ThinkSpeak stores, visualizes, and provides an API to access real-time and historical analysis. And the web-based dashboard allows the stakeholders to monitor live data, and make data-driven decisions. For hardware components, we tried to keep it low cost, so that's why we use ESP microcontroller as a central unit for the data, DHT22 to measure temperature and humidity, LDRs to monitor light intensity, anemometer which measured wind speed, BMP 280 which captured atmospheric pressure, GP 210 which is known as the dust sensor which measured PM 2.5 and PM 10.0 concentrations, and uh, all of the sensor data were sent to the ThinkSpeak API again, and the ThinkSpeak collected all the real-time data and showed it into a dashboard. So here you can see our schematic diagram. This shows all the connections that were used to conduct the IoT to make the IoT model. And this is the dashboard that was created. This dashboard is then again created through the ThinkSpeak platform. Here we can see all the analytics, how much temperature is there, how much humidity is there, air pressure, dust particles, the air quality index as well. Sorry. Oh, okay. Yeah, and the heat index as well. For methodology and application, what we did was initially the IoT weather and dust monitoring system was deployed in rural Bangladesh for 3 months, and the sensors were placed strategically in the fields. And and the sensors monitor dust, temperature, humidity, wind, and light to assess the crop health, optimize irrigation, and predict pest infestations. And farmers could access the real-time dashboard to visualize the trends, and they received alerts which enabled adaptive farming process practices. And for irrigation and pest management, the accuracy caused real. So basically, there was accuracy for irrigation and pest management, and the real-time data allowed efficient water use and early warnings for pests and diseases, improving crop health. Here we can see the results that we found throughout the 3-month period. And here, the pilot implemented showed improved irrigation, pest control, and resource management. Real-time dust monitoring helped farmers to take preventive measures against pollution. Dust levels spiked during calm and dry periods and decreased with higher wind speed. And the temperature followed normal daily cycles. Multi-parameter data provided actionable insights for adjusting farming practices based on wind, dust, and humidity. Farmers reported the system was user-friendly, reliable, and enhanced agricultural resilience and productivity. In conclusion, uh, basically, our IoT weather dust monitoring system provided a real-time localized data on dust and weather conditions, enabling farmer to make informed decisions to improve irrigation, pest management, and crop yields. And the employment showed that even with minimal training, farmers could leverage the dashboards and alerts to save water and protect crops. Its low cost, easy to install design made it suitable for rural areas in developing countries, promoting climate resilience and suitable farming. For future work, we thought of adding soil and advanced air pollution related sensors, and for longer deployments across regions and predictive analytics using machine learning to further enhance the decision support system and farm productivity. Thank you. If you have any questions, you're welcome to. I'm welcome to. I'd be happy to answer.
Okay, Maureen, you used half of the time you have for your presentation. Okay. Questions, comments? You mentioned that you have one pilot system.
Yes.
What it means exactly?
It means that we implemented the IoT sensors into a rural area in Bangladesh for 3 months, and we collected data from there. And for using those data, we actually showed the real-time data in our dashboard, and we also have graphs and charts for those data. So this data, which is shown here, this is for 3 months. This is the trend for almost 3 months.
In which period was of the year?
It was during our winter season that started from January. That is that is typically December, January, and February.
In this period was relevant for do this test?
Sorry.
Why in these months of December, January, and February was relevant for doing the test and nor in August, September, or April?
Yes, we were able to extract only 3-month data, and after that we plan on publishing the paper. But we are actively taking the data. The sensors are still recording the data from the atmosphere. So we plan to publish a journal later with all of with 1 year data. Uh, and we plan to show more analytics of the parameters and predictive analysis as well.
More than for publication times, not for the specific weather condition in December, January, and February.
Yes, we integrated the sensor throughout the November, and last year on December, January, and February, we integrated the sensors into the rural areas. So after that, we started working on the paper, and we thought, why not submit the paper somewhere? And then
There is not weather reasons. There is not, because in these months is when more sad or high wind there are, not meteorological or weather reasons.
weather reasons. Basically, we didn't pick a month specifically. What we did was we after we were done integrating the sensors, after that we planned on installing the device. So um, that's how we started working on December. We didn't have a specific. We didn't have the intention to catch any specific weather and then implement it on those times.
Okay, there is no relevant reason since the point of view of the specific application you speaks. Okay, and you mentioned as well in the abstract of your paper that the system helps improve agricultural productivity and sustainability in the face of climate change and environmental pollution, contributing to the socio-economic development of Bangladesh rural farming communities. This is a very, very strong statement, but you don't provide data that support this statement. Perhaps you can explain a bit about the reasons you say that.
Okay, thank you for the question. Basically, in our country, in the rural areas, basically these parameters are not usually measured. It's not a common practice to measure these parameters and help the farmers in our country. So, if we our plan is to extract the data to our IoT sensors, and then we plan to provide these data analytics to the farmers, and this would actually help the government as well. So when the farmers will start doing well, when the when it, the our
Listen to you, Maureen.
I missed
We missed you.
we missed sorry.
We listen you now. Please,
Okay, okay.
you can repeat a bit because we lost when you were explaining.
Oh, I'm so sorry. Yes, yes, yes. So basically, what I was saying that in our country, in rural areas, it's not a common practice to extract all this sensor data and through an IoT sensor, and then provide analytics to the farmer to help them in farming. So in our country, farmers just assume, and they use the traditional farming system. They don't have any monitoring system. So what we plan to do in long term is we plan to provide this data to the government, and we plan to expand our IoT sensors throughout the country. So we want to create a hub of sensors, and then install and then store all the data in a cloud server. So that way our the cloud server will contain all sorts of environmental data related to farming for different areas into the cloud server, and this will help our government to monitor all the farming systems in rural areas and implement policies in our country. So in long term, we aim to do this.
It means that in your current work, this situation is not, but is a plan that it depends of diverse persons, institutions, government, the participation of government trying to implement this kind of policies. Okay, and perhaps how long you think you need for implement this kind of systems, and how much it can cost dollars
So we're trying.
for understanding
Thank you.
all.
Okay, thank you. So basically, uh, we are low at workforce right now, but I am gathering more students who are interested in working this project. So what we plan to do is we plan to make more devices related to we plan to make more devices which will contain IoT sensors, and they will extract the environmental data. So in long term, what we have to do is we're planning to make PCBs, and then we're just going to install the PCBs into multiple rural areas. So I think it's going to take some time, because we have to identify the rural areas as well, because currently we have just implemented our IoT device into just one specific rural area. So what we have to do is we have to identify the rural areas, and we have to install those devices on those areas, and we have to take feedback from the farmers if this device is being helpful or not, because currently we just took feedback from few farmers. So I think it's gonna take 1 to 2 years to install and take feedbacks, also to cover all the areas in our country.
It sounds small time for, I don't know how wide and large is your country, but 1 2 years sounds at least a short time, or is quite effective the action of the government, of the national government. And in $1 million, how many $1 million think you could spend doing that?
Basically, I haven't thought about it. I think I have to look out for funds. Currently, my university is funding me, so I have to pitch my university to get more funds to in order to create more devices. And I have to identify the rural areas at first, and after that, I'll get to know how much device I have to make, and I have to pitch it to some investor regarding funding. So currently, I have received a VC fund from my university, so I can use that as well. That is worth $2,000, and I am working with professors at my university. They also are interested in investing the funds here. So maybe uh also I think I'll be applying to government funds as well, because my professor also mentioned that government provides funding to these to those projects which will be beneficial for the country.
Because I see in Wikipedia that the population in your country is
Yes.
120, almost 123 millions of people. So
Yes,
it's
yes.
quite a big country.
Yes.
So I think you need do one fair evaluation about the efforts need for do this in your country. Okay, thank you
Yes.
very much for your presentation and for your
Thank you so
contribution,
much.
Maureen.
Thank you. Thank you.
So this way we end this session. Thank you very much for your participation to all.